Good afternoon. So I'm here to talk about reconstructing training data from document understanding models. I'm Jérémie, and this is a joint work with Arnaud and Aymen at Crédit École. So Crédit École is a bank. One thing we do is to train document understanding models on sensitive data. This can be some ID cards, passports, bank check, that kind of document. Something common here is that it's multimodal. There is a text, but also a layout and an image. And the meaning of the document really lies at the interplay between the text, the layout, and the image. And this is why the neural network we train on these documents are also multimodal. So in a nutshell, they have a bird, which is a text encoder, some 2D position encoding for the layout, and some visual feature to encode the image. And with such model, we do some discriminative tasks. For example, token classification, document classification, information extraction. It's that kind of discriminative task. And you have an example here. You take an ID card and then you classify, this is the name, this is the surname, the document ID, and so on. So this is the kind of thing we do. However, there is this paper which was published here in 2021, which says that if you take a language model and you train it on sensitive data, then if you have access to the language model, you can extract the training data. It's a major privacy leakage. And moreover, 2 years later, there was this paper saying that it's significant. There is at least 1% of the training data which are memorized and can be extracted by an adversary. So this is huge. This is something that we cannot ignore. This paper were on a large language model. So the question we ask in this paper is, can similar attack be developed on our light document understanding model? So this is the question we answered in the paper. For this question, there are 3 aspects to consider. First, it did not exist. In the literature, there were no attacks against this class of model. Second, as I said, our models are multimodal. There is the text, the layout, and the image. And it wasn't clear if that would increase or decrease robustness, because on the one hand, it makes the interaction more complex. So maybe it's also more complex for the adversary. But on the other hand, it gives more space in the model for memorization. So it wasn't clear. And third, our document understanding models are encoder only. This is because we are doing some discriminative tasks. So the models are not designed to generate content. And so it's harder to make the model recitate the training data. And this is a major difference with the large language models that were attacked before, because these are decoder only. They have a mouth, they are made to generate content. So the adversary can make this model recitate the training data. So it was known from the literature that encoder-only models are harder to attack. And so this is why it wasn't clear if such attacks were credible on our models. So the short answer is yes. It's possible to do some privacy attacks against the models. And this is what we did in the paper. So here is the intuition of the attack. So you start with a document which is partially anonymized. So there are some fields which the adversary do not have access to. And then we choose a target field, which is the green one here. And the adversary will try to reconstruct, to guess what was there during training. First, as I said, the model is not able to generate content. So at this point, we have to leverage an auxiliary model. This model generates some candidates. For example, if we are trying to reconstruct a date, the auxiliary model says these tokens are likely for a date, so they are candidates. Then we use the intuition that the model was trained to minimize a loss. So if we find a token among the candidates which has a very low loss, it's likely that it's because the token was there during training. So we evaluate all candidate tokens and measure the loss. And we say that the one with the minimal loss is likely to be the token that was there during training. And so we say exactly that. We put this minimal token here, and we iterate until we have inverted the whole field. So you have the idea of the attack. In practice, we had to implement a lot of heuristics to make it work on real data, but this is the intuition. So now, how do we get in practice? So here you have some examples of reconstructions in our datasets. So each line is a field that was reconstructed from the training set. So there is a wide variety of reconstructed fields, some numbers, some dates, and so on. I want to highlight that this is perfect reconstructions. So in this setting, the adversary was able to reconstruct exactly the token sequence from the training set. And in our best setting, we were able to reconstruct up to 4.1% of the training set. So it's meaningful. There is a significant part of the training set which is memorized. Moreover, we tested it in a wide variety of settings. We used 2 different datasets, which are quite standard for document understanding, 2 architecture, which again were state-of-the-art when they were published, and 4 tasks. And in every setting, we were able to reconstruct a meaningful part of the training set. Okay, now we did some ablation to better understand what's going on. The first one is about overfitting. Is it only overfitting that we are measuring? And the answer is no. And here is an experiment we did. So we take a model and we're training for very long, like 300 epochs. So of course, at the end, the model is overfitting. You have 2 points, the checkpoint with the best validation accuracy and the checkpoint with the best validation loss. And then the x-axis is the performance of the attacks. It's the comparison with the baseline. And so when it's above 1, it means that we can reconstruct a meaningful part of the training set. And what we observe here is that well before overfitting, the attack works. We can extract some content. So it demonstrates that overfitting is not necessary. Of course, it makes things worse, but it's not necessary. And in fact, this is consistent with some other work that was published before, but we observed that it was consistent with our experiment here. We did some other ablation. I recall that we have 3 parts: the text, the layout, and the image. One question is, where is the memorization? And for example, does the image contribute to memorization? And so to verify this, we can remove the image from the model. And what we can see is that if we remove the image, the performance drops, which means that there are some pixel token association within the model and that the adversary can leverage for the attack. And we can even go further. We say we have removed the image, now let's remove the layout. And it's the same idea. If you remove the layout, the performance drops, which means, again, that there are some association between the layout and the token, which contributes to memorization. So we did some other ablation, but I prefer to conclude here. First, document understanding model memorize some training data. In this paper, we implemented the first attacks against this class of model, so it worked. Second, the attacks are realistic. Even if you have a good pipeline with no overfitting and deduplication, it's likely that your model will still memorize some content. And third, multimodality is a factor of risk. If you have the choice between a pure text and a multimodal model in a setting, you really should take this into account when deciding which architecture to choose from. Okay, and now there are some research directions. For example, we did these experiments on fine-tuning, but it could be interesting to do the same on pre-training. And on a broader scale, I think deepening our understanding on what is memorization and why it happens, that would really benefit the security community. And thank you for your attention.
Thank you.